As pollution from coal and petroleum become more and more severe, problems such as climate change arise. Using renewable energy significantly reduces the amount of pollution we produce and reduces our dependency on oil or gas imports. Our team was tasked to design, build, and test a wind turbine. The main objective was to produce the maximum amount of power at a stated tip-speed ratio while minimizing the mass of the turbine. The turbine should be capable of self-starting at a wind speed of 10 meters per second, have a tip-speed ratio between 3 and 8, and a maximum diameter of 500 millimeters. The maximum angular velocity should be less than 3,000 rotations per minute, and it must weigh no more than 500 grams. With this in mind, we began investigating how to maximize the power output, maintain structural integrity, and minimize mass. Here, we will walk you through our thought process as we designed, manufactured, and eventually tested our wind turbine.
From theory, we know that the longer the blade, the greater the amount of energy extracted from the wind. In order to maximize rotor torque, we had to select an airfoil with a high lift-to-drag ratio and then determine the angle of attack for which this ratio is maximized. We initially shortlisted the SG6043, BW3, and E62 airfoils. While the BW3 and E62 have relatively high lift-to-drag ratios, we selected SG6043 as our primary airfoil for its desirable lift-to-drag ratio, good stall characteristics, and thickness. For our chosen airfoil, the angle of attack that maximizes lift-to-drag ratio is approximately 8 degrees. Due to the difference in rotational speeds at the tip and root of the blade, twist is applied along the length of the blade. Both the Betz and Schmidt's equation provides a basis to calculate chord length and twist. Unlike the Betz equations, Schmidt's takes into account the rotational wake generated when air flow past the blade. Working with these parameters, we use the Schmidt's equation to generate optimum chord and pitch distributions for both the 2 and 3 blades design. Using Q-blade to simulate the performance of our designs, we realized that the 2-blade design would need to run at TSR 5 to achieve the same power as the 3-blade design at TSR 4. We agreed that we should adopt a 3-blade design with TSR 4 because this produces good power output without compromising structural integrity. Furthermore, according to our initial mass calculations done in Creo, we found that a 2-blade design would actually be heavier than a 3-blade design. The 3-blade design, with the same performance at the lower mass, would result in a higher merit factor. The choice of the blade tips was inspired by scimitar propellers. Sweeping the blade tip back allows the turbine blade to cut through the air more efficiently.
The main purpose of the structural design was to maintain total stress values under the critical stress value, while maintaining small deflections. Since certain idealizations are being made to make calculations easier, such as us not considering the weight, which we believe to be a good assumptions to make for short periods of time. Why? Because the weight is negligible when compared to the aerodynamic resultant force or the centrifugal force, and would only affect the fatigue as seen in aerodynamics of wind turbines by Hansen. Also, the moment of centrifugal stiffness was not considered, which is not technically correct because IYZ is not 0. Torsion also was not considered, shear was not considered, so we needed a good safety factor. For the purposes of this application, our safety factor was 5, which we deemed to be sufficient. The method outlined in the lectures was followed in order to evaluate the structural integrity of our blades. We based our analysis on cantilever beam theory, idealizing the blades as simple cantilever beams with varying cross-sectional area and stiffness, and constant Young modulus, focusing on calculating the stresses and deflection due to aerodynamic forces and the inertial forces. All the dimensions needed for the cross-sections, such as the thickness, chord, second moments of area, etc., were obtained from Xfoil and Creo parametric, while the CL and CD values were obtained from the Q-blade simulation. Certain limitations are worth mentioning. The integration method used is basic trapezium rule, which is not very accurate at low number of sections, 20 in our case. From the graphs, we can see that the stress values and tip deflections are satisfactory, which would allow the turbine to perform its aerodynamic purpose without being compromised structurally. We all agreed that a circular route would increase drag, but it would be better structurally. Our choice for a thicker airfoil provides less drag and is satisfactory from a structural standpoint. The same airfoil family was chosen to facilitate better blending. Also, in this fashion, we would obtain more torque at the root. As far as self-start is considered, we believed that we only needed the moment due to the aerodynamic forces to be greater or equal than the friction moment of the gears. From our simple estimations, we met this criteria.
The turbine was designed using Creo-parametric and Q-blade. Whilst blade design was still underway, we began designing the hub and nose cone sections. As the hub is only used for connecting the wind turbine to the shaft, it will not be subjected to large stresses. After checking material constraints, such as the smallest thickness possible to manufacture, we finalised our design, which featured a very thin hexagonal shape with large holes along the surfaces, minimising its mass. After researching nose cone designs, we agreed that the nose cone has a relatively small impact on the overall performance due to the turbine's small scale. Therefore, the cone is designed to be hollow and shallow to minimise mass. The curvature on the surface was chosen to adhere to the hack series for reducing drag. We considered this to be a major uniqueness of our design. After determining the optimal twist and chord distribution of the blade, we exported 20 sets of spline points from Q-blade. These splines were blended and the root was extruded into the hub. Due to the limited resolution of the 3D printer and to avoid weakness during printing, material was added to both the trailing edge and the tips. Due to the limitations of the size of the 3D printer, we calculated where the stresses along the blade would be at a minimum and cut our design into 4 parts at those points. These were printed separately and would be glued together during assembly. The cuts on the blades were designed to be of a dovetail shape. This allowed the blades to be attached to the hub in a secure manner. Piecing all of these parts together, we had a finished design ready for manufacturing.
The hub was manufactured via 3 processes: turning, milling, and broaching. Utilizing a lathe, the block of cylindrical aluminium was trimmed down. Then a hole was drilled in the center of the block using a tailstock. With a vertical milling machine, the cylinder was cut into the desired hexagonal shape. We then drilled the holes for minimizing mass onto the corresponding surfaces according to the coordinates entered. Finally, the keyway was produced by broaching. The blades and the nose cone were manufactured using a 3D printer via a diffusion deposition method with ABS plastic. The 4 printed parts are then glued together. Extra material was sanded off the turbine to match the shape we desired. This process is assisted by 3 templates of laser-printed airfoil cross-sections at different locations along the blade. We consider these templates used for sanding another uniqueness for our group design, as it increased our manufacturing accuracy massively. The turbine is now ready to be tested.
Our manufactured wind turbine had a mass of 115 grams, slightly lower than our design mass of 119 grams. After a tense few minutes, the wind turbine successfully self-started at a wind speed of about 9 meters per second. Unfortunately, the maximum power output occurred at a TSR of 5.4, which was higher than our design TSR of 4. However, the RPM at this maximum power was around 2,500, well below design specifications. A considerable tip deflection can be seen when being run at higher wind speeds. Because of the occurrence of stall behavior and flow separation near the tips, the performance of our wind turbine was affected significantly. We believe that the tip deflection was far greater than we had anticipated because of the higher RPMs, 4,200, where we estimated a tip deflection of 2 mm for an RPM of 3,000. During testing, we also heard a short, loud interference that we believe to be due to aeroelastic response of the blades. Thankfully, this caused no issues, and we continue to test at wind speeds beyond this point. Here you can see a plot of the coefficient of power against TSR for all testing regimes, showing a maximum CP of 0.196 occurring at a wind speed of 12 meters per second. We believe that the power coefficient could greatly be improved.
Obviously, further mass reductions of the turbine would be an improvement. While the nose cone and hub are already small, further efforts and improved manufacturing methods could reduce mass further. The ability to manufacture hollow blades with an I-beam structure, as commonly used in the industry, would also enable a lighter design. Vibration analysis can be carried out on our turbine via computing the eigenfrequencies of the turbine numerically. In an effort to prevent flow separation, vortex generators could be added onto the surface of the blades. This, however, requires some sort of flow visualization in order to be aerodynamically effective and not simply added mass. This is beyond the scope of our knowledge during the design stages. Nonetheless, our turbine performed admirably and beyond our expectations. We are very happy with it. Thank you for watching and goodbye.